Hi there, everybody. Welcome to another Chem Complete lesson for the ethers in Organic Chemistry 2. Last time we took a look at how to name ethers and an introduction to ethers, and this time we're going to start looking at the synthesis behind ethers. So if I would like to create an ether, how do I go about doing that? There's really two major ways we're going to consider. We'll talk about the other one in a separate lecture, but today we're going to focus on by far the most popular and common method, which is the Williamson Ether Synthesis. And you may see Williamson Ether Synthesis abbreviated sometimes. And so you'll see it abbreviated as WES, very common. The Williamson Ether Synthesis is a very, very simple SN2 type of mechanism for creating ethers. So what we require is an alcohol, and we will require an alkyl halide, which I'll represent as RX. Just a note here, you could have a tosylate here. It's basically you need a good leaving group, which most commonly we use halogens, but tosylate is certainly a good leaving group. It's even better than the halogens. So the major requirement here is that this R group is going to need to be primary or methyl. And the reason for that is you want to avoid potential E2 reactions. So if you remember back when we talked about substitution versus elimination, if we had strong bases and we had secondary leaving groups, we would start very readily eliminating instead of substituting, and we need a substitution to occur in this case. So let's take a look at the individual steps. Number one, we're going to take an alcohol, which we know is a amphoteric substance. And with that alcohol, I'll just go ahead, I'm going to keep the example simple. We'll use methanol to start. All right, CH3OH. I'm going to subject this alcohol to a deprotonation. Keep in mind, unless you're dealing with phenols, which have that extra resonance stability left behind, you need a very strong base. Sodium hydroxide is not going to cut it here. So we're usually looking at sodium or some form of sodium hydride. I tend to use a hydride form. Remember that hydride produces H-, which is a very strong base. That's what a hydride is going to give you. And this will deprotonate the alcohol into the alkoxide form. So we talked in the last video about alkoxy substituents when we were naming them. All right, this is what would be known as an alkoxide ion. Very, very good nucleophile. So this is a good nuke. It is also a fantastic base. So we'll also say it's a good base. In fact, it's going to be a slightly better base than it is nucleophile, and that's exactly why we need to avoid secondary leaving groups, because that would start promoting an E2. If I had this acting as potentially a nucleophile, it's going to behave more as a base when I get secondary leaving groups. Again, go rewatch those videos if you need a refresher on SN2 versus E2. So great. I deprotonate this. I have my alkoxide ion. Just for those of you interested in the mechanism, this is again following a simple SN2 mechanism at the end of the day. But the hydride would take this mildly acidic proton, and these electrons would go over to the oxygen, and that's what's creating the alkoxide ion. So that's step one in the Williamson ether synthesis. Right? Step two is that once I have my alkoxide ion, which I'm going to utilize as a nucleophile, I'm going to go ahead and at this point I will add in step two, my leaving group. So let's go ahead, we'll use a simple just methyl as well for this initial example. So methyl iodine, right? Methyl iodide, iodine is a good leaving group. So the only thing that's going to happen here is that the iodine will leave, the alkoxide will come in and substitute. Again, same time, because we're dealing with an SN2 type of mechanism. And then I have my ether. I have my resulting ether. So this is probably one of the simplest versions, if not the simplest version, of the Williamson Ether Synthesis. All right, so I'll give you guys another example where I turn around and I would have, this time we'll make the alcohol a little more complex. So let's say CH, and then we've got a CH3, right? And then down here we've got an OH. So this is the alcohol of interest this time. We're looking at 2-propanol. Step 1 is going to be the deprotonation. Again, you may use just regular sodium. You also may see, I'll write up here, NaNH2, this amide reagent can be used. So keep that in mind. Just a very, very strong base is what you're looking for. So I tend to stick with the the hydrides, not hydroxides. Going to deprotonate this. And so what I end up with is an alkoxide ion that looks like this. Keep in mind the oxygen has 3 lone pairs around it once it's deprotonated, because it's taking that extra set back from the hydrogen. And so now, in step 2, I can pick out, again, a primary or a methyl leaving group. I'll go again with a methyl leaving group. We'll do bromide this time. The bromine leaves, the alkoxide attacks, and then we end up with CH3, C. Now this C still has an H, right, that's attached up here, and that O is now a methoxy group because this oxygen attacked this methyl, and then CH3. So this would be the resulting ether compound that would come out of that Williamson ether synthesis. All right, now one of the things that is interesting with the Williamson ether synthesis is that whenever you're dealing with this, you always, if you were to look at the ether at the end of the day and you want to sort of what we would call retrosynthetically analyze it, so retro meaning going back to and pulling apart the ether, you always want the leaving group to be in the less hindered position. So I'll give you an example here. Let's say one of the naming examples we did was methyl ethyl ether, right? If I wanted to create this from an alcohol and an alkyl halide, what would the 2 reagents be? What would my alcohol be and what would my alkyl halide be? So what I do is I split it down right where the oxygen is, and I say, well, I've got a methyl group and I also have an ethyl group. So pretty close call this time. Well, the ethyl group, this position, whatever's attached to this CH2, is going to be in a primary position. Whatever's attached to this methyl is going to be in a methyl position. So remember, the goal is I want the leaving group to be the least hindered. I can have a slightly hindered alkoxide ion. I cannot have a hindered leaving group because this is, again, SN2 mechanism when we look at the nature of the Williamson ether synthesis. So if I analyze this and break it apart, I would say the methyl is where I want my leaving group because methyl is less hindered than primary is. So I would say, all right, I'll start with CH3I for this guy, and this will be the alcohol, right? So if this is the case, I would say, all right, CH3, CH2, OH, I'll subject that to NaH. I'll get my alkoxide ion. I'm leaving off the lone pairs for time's sake. And then I would use my methyl iodide, and I would end up with my ether. Now I'm writing this out in the condensed formula. But this right here is the same thing as the guy that we had right up here. So this process is sort of going back. If I have the ether, I'm breaking it apart and I'm sort of analyzing it retrosynthetically. All right. So here are 2 other examples, and I want you guys to try these. So let's go ahead and we will use this ether, right? And I think that's another one we may have named. We'll stick with the ones that we were naming, how we would create those. And then let's try that. So pause the video, okay? See if, and it's great if you write out the reagents, but see if you can figure out, when I split these apart, which starting piece needed to contain the alcohol and which needed to contain the alkyl halide. So pause the video, try to break these pieces apart and sort of retrosynthetically analyze this, and then come back and see how well you did. So I'll see you guys in just a second. All right, welcome back. So if I break this guy apart right here, I'm going to see that I have a phenyl group, and then I also have an ethyl group, which is over to the right there. So the question is, which one better suits the alcohol? This is primary, whereas this would be aromatic. And so the aromatic being a larger group, and not to mention that leaving groups directly on aromatics are not going to do a good job in terms of leaving. If it's a benzyl position, remember that benzyl, I'll draw this up here, has an extra CH2. Benzyl leaving groups are excellent. So if I have a bromide here, but notice there's an extra CH2 in between the ring and the bromine. And that's different than placing the bromine directly on the ring, because this plus charge that's left behind can be resonance stabilized by all of these different positions, right? So that's very different than putting the leaving group here. So I would definitely want phenol as my alcohol, and then my leaving group would be in the primary position. So these are the two that I would want. I would subject this to NaH. Technically, just letting you guys know, technically if you use sodium hydroxide here, that would be okay in this case, because phenols are more acidic, so they don't need a super strong base. They just need a fairly strong one to deprotonate. You should make a habit of just sticking with the sodium hydride or whatever your very strong base is in each of these situations. It just makes for good practice so you don't forget going back and forth, right? So I have that, then that will react with the ethyl iodide, and I'll end up with the proper product, which is my phenyl ethyl ether. So same thing, hopefully you realize if you're breaking this guy apart, you have a methyl group and you also have a T-butyl group. T-butyl group is very bulky. That carbon is a tertiary position. So definitely not a leaving group on this carbon here, because these are SN2 mechanics. We're going to keep T-butanol, and we will have methyl iodide as the two pieces. So again, you would deprotonate your T-butanol with a strong base, send that alkoxide, that T-butoxide group, in to attack the methyl and kick the iodide off. So that's really the Williamson ether synthesis as a whole. Deprotonating alcohols, sending them into either methyl or primary alkyl halides for a SN2 reaction, and you get ethers out the other end. So very common reaction. Most labs go through this when you're dealing with organic chemistry too. And that's pretty much it. So that covers Williamson ether synthesis. There's one other ways we're going to take there's one other way, excuse me, that we're going to look at for creating ethers after we get through the rest of this. So that is it for Williamson ether synthesis, and I will see you guys for the next video. Please remember to comment if you have any questions, or if you like the video, please give it a like and subscribe. That really helps me out and I appreciate it. And other than that, I will see you guys for the next lecture, where we will wrap up how to create ethers using synthesis. So I'll see you guys there.